Hi everyone, and welcome to our final presentation for Cinch 468 Software System Scalability. My name is Vinayak, and along with my teammate Patrick, we have developed SIFT, the Distributed Semantic Retrieval System. In today's world of massive data, traditional keyword search often falls short because it only looks for exact character matches. We built SIFT at the University of Victoria to explore how we can use modern distributed architectures to make document search more intuitive and, more importantly, horizontally scalable. So, moving on, what exactly is SIFT? At its core, it allows users to upload PDFs and search through them using natural language. Unlike traditional systems that rely on keyword matching, we use vector search to find semantic meaning. This means the system finds what you mean, not just what you say. To ensure that this remains fast as the number of users grows, we implemented three core architecture pillars. First, asynchronous processing. Uploads never block the API, the heavy lifting happens in the background. Second, the stateless API. Any replica can handle any request, which is essential for horizontal scaling. Third, vector database. We use qdran to handle the complex mathematical searches required for semantic retrieval. Architecture is designed as a containerized microservices system. As you can see in this diagram, we use Nginx as a reverse proxy and load balancer to route traffic to our fast API replicas. When a user uploads a document, the API doesn't process it directly. Instead, it stores the file in MinIO object storage and sends the task to a Redis message broker. This decouples the API from the CPU-intensive work performed by our Celery workers. These workers handle the text extraction using PyMu PDF and generate embeddings using the all-mini-LM L6v2 model. Finally, the resulting vectors are stored in qdran while the document metadata is kept in PostgreSQL. This separation of concerns allows us to scale the compute-heavy workers independently from the user-facing API. So, why this architecture? Every choice in the stack was made with horizontal scaling in mind. Firstly, asynchronous tasks. By using Celery and Redis, the API can return an immediate HTTP 202 accepted status. This prevents the API from hanging while waiting for an expensive CPU processing. Second, statelessness. By externalizing all the state to MinIO for files, PostgreSQL for data, and Redis for tasks, we can spin up as many API instances as we need without worrying about the session affinity. Thirdly, vector optimization. We choose qdran over traditional relation databases because it uses approximate nearest neighbor search. This is significantly more efficient for searching through thousands of embeddings at scale compared to the brute force distance calculations. So now, you might be thinking how a PDF becomes searchable. Let's look at the life cycle of a document in our system. Firstly, the upload happens. The client submits a PDF, the API validates it, and immediately returns that 202 status. The API never waits. Second, in queue. The metadata is pushed to Redis, and the file reference is stored. Third, the worker fetch. An available worker picks up the task and downloads the raw PDF from MinIO. Fourth, the embedding process. This is where all the heavy lifting happens. We extract the text, split it into chunks of roughly 1200 characters, and then convert those chunks into high-dimensional vectors. Lastly, the indexing. Those vectors are indexed in qdran, and we update the status to ready in PostgreSQL. The document is now officially searchable. Next, how a query becomes a result. When a user performs a search, we use a unified vector space. This means we use the exact same embedding model for the query as we did for the document chunks, ensuring they exist in the same mathematical space. The API embeds the user's natural language query and sends it to qdran for an ANN search. We retrieve the top 5 most relevant chunks and return those ranked results to the user. Importantly, we have implemented secure multi-tenancy. Results are strictly filtered by the user ID at the database level, so users only ever see their own content. Now, let's look at SIFT in action within a local development environment. You'll see our secure sign-up and login flow, followed by the PDF upload process. Notice how the UI provides real-time status polling since the processing is asynchronous. The user can see exactly when their document moves from processing to ready. Once indexed, we can perform natural language queries and see the system return the most semantically relevant sections of the uploaded documents. I'll now hand it over to Patrick, who will walk you through the performance testing and how the system behaves on the UVic virtual machine.
We scaled concurrency from 5 to 20 users for each of the 3 scenarios, which allowed us to better observe how our system behaves under increasing load, and in turn helped us identify where performance degraded first. For evaluating scalability, we first tested locally using the Intel i5 16GB RAM Windows machine, which ran WSL Ubuntu. Then we deployed the system to our group VM, which introduced stricter constraints such as unlimited CPU support and less host-level tooling. For simulating a realistic load, we first ran our warm-up scripts and then used Locust as our distributed load testing tool. Locust was helpful for modeling concurrent user behavior in a controlled and reproducible way and helped address common testing pitfalls like incomplete coverage or unrealistic single user benchmarks. When running locally, we ran our load tests via Python env on WSL, but on VM we instead ran Locust within the Docker network due to user restrictions. We designed 3 workload scenarios. The first was concurrent uploads, where multiple users upload documents concurrently to stress the ingestion and embedding pipeline. Second was concurrent searches, where users continuously issue semantic queries against indexed documents. And third was mixed workloads, to better simulate more real-world activity by combining uploads and searches. Here's our benchmark summary across both environments at 10 and 20 concurrent users. In terms of reliability, we observed 0 failures across all tested scenarios. For search latency, the VM results were slower than local, but still remained within 2 seconds at P95. Locally, search remained much faster, staying around 100 milliseconds, a few hundred milliseconds, even at higher concurrency. Behavior was more mixed at upload except latency. VM upload P95 remained low at both 10 and 20 users, but local 20 users run showed a much larger 3.7 second spike for P95. We assume this is likely due to host-side resource contention and measurement variability in the WSL-based setup, rather than a change in application logic. Finally, for time to ready, we see a clear scaling trend. As concurrency increases, processing time rises substantially, especially on the VM, where it reaches roughly 1 minute at 20 users. This aligns with our later profiling results and indicates that the bottleneck lies in the background worker processing rather than the API layer. So overall, the system remained reliable and kept search latency within target, but asynchronous processing time increased significantly as worker load grew. We generated our flame graph by attaching PySpy to a worker container. It showed that most worker execution time is concentrated in the embed text function. This corresponds directly to the sentence transformers embedding step, which suggests embedding generation is the dominant computational cost. On the right, we plotted CPU utilization over time across system components after capturing a Docker stats time series for 20 concurrent users. It showed us a clear resource imbalance. Worker containers consistently reach over 800% CPU utilization, fully saturating all available cores, while the fast API layer and qdrent vector DB remained largely underutilized. This disparity indicates that the system is not limited by request handling or database performance, but by the compute-heavy embedding stage. This evidence leads us to believe that SIFT behaves as a worker-bound distributed system, where throughput is constrained by the rate at which workers can process embedding tasks, rather than the capacity of the API layer. This helps to explain the increased time to ready observed under higher concurrency and highlights the primary limitation of the current design. Based on our bottlenecks, we implemented a few optimization strategies. First was a chunking strategy. Initially, small chunks created a large number of embeddings, which significantly increased CPU load. By increasing chunk size and reducing total embeddings per document, we were able to lower processing overhead and achieve more stable throughput across both environments. Second, we focused on scaling workers. Since our analysis showed the API was not the bottleneck, adding more API replicas had little impact. Instead, we scaled worker instances, which improved ingestion throughput under concurrent uploads and allowed for better utilization of available CPU resources. Third, we introduced warm-up scripts to address cold start effects. Without warm-up, initial requests would include model loading and cache initialization overhead, which distorted early latency measurements. By preloading the system, we achieved more consistent and reproducible benchmark results, particularly for P95 latency. Despite these improvements, time to ready still remains CPU bound due to the cost of embedding generation. We encountered a few engineering challenges along the way. The first challenge was VM compatibility. Some dependencies like NumPy and Minio relied on CPU instructions that the VM did not support, leading to build failures and crashes. Resolve this by pinning compatible versions and fully containerizing the stack to remove host dependencies. The second challenge was async debugging. Because processing happens in the background workers, failures were not visible to the client, which caused documents to appear stuck in a processing state. We address this by adding structured logging and enforcing explicit state transitions, from pending to processing to ready or error. And lastly, we encountered a design trade-off and chunking strategy. Smaller chunks improved retrieval quality, but increased the number of embeddings and CPU cost. Through iterative testing, we selected a balanced chunk size that maintained quality while keeping processing time manageable. Alongside solving these challenges, we also had several assumptions that didn't hold in practice. For API scaling, we expected that adding more replicas would improve performance. However, our measurements showed minimal impact on latency or throughput, confirming that the API layer was not the primary bottleneck. For chunking, while smaller chunks were expected to improve precision, in practice they significantly increased embedding cost with only limited observed improvements in results. Finally, for load testing on the VM, we initially attempted to run Locust directly on the host, but due to environment constraints, this was not viable, so we moved to a containerized setup within the Docker network. The key takeaway was that these decisions were validated through measurement, which helped us avoid optimizing the wrong parts of the system. So to conclude, SIFT demonstrates that semantic search can be implemented as a distributed and horizontally scalable system. From our testing, we found 0 request failures across all tested workloads and had reproducible benchmarks. The stateless API design and containerized deployment allowed the system to scale cleanly at the infrastructure level. At the same time, our evaluation identified important limitations. Embedding generation remains CPU intensive, and as concurrency increases, time to ready scales with workload. While the worker layer was the primary bottleneck in our tests, this does not rule out additional constraints emerging at higher scale. If continued further, we could explore GPU-accelerated embedding generation, batched processing, or scaling workers' nodes more aggressively. There's also room to explore lighter or quantized models to better adapt to CPU-constrained environments. Overall, our results suggest that the system scales well within our tested range, while highlighting clear opportunities for future optimization. Thank you for listening.